Welcome everyone to this webinar titled Well Modeling Applied to Geothermal Resource Evaluation. This series is brought to you by the GEODE consortium, which is led by Project Interspace and the Society of Petroleum Engineers and is funded by the U.S. Department of Energy's Geothermal Technologies Office. My name is Deanna Morrison and I'm your facilitator. It's now my pleasure to welcome our moderator, Dimitri Zunde, a geologist with 15 years of expertise in the oil and gas and geothermal sectors. Currently, he works as a geoscience advisor at the Gaffney Klein Energy Advisory, Baker Hughes across Europe, the North Sea, and the Caspian regions. Dimitri holds a master's degree from Royal Holloway University and a PhD in geoscience. His areas of expertise include subsurface modeling, reservoir characterization, and resource assessment. I'll turn it over to you now, Dimitri.
Thank you, Diana. I'd like to thank the consortium for their support to develop this web event. And I'm now pleased to introduce our first speaker. Our first speaker, Yamal. He is an experienced reservoir engineer with 26 years of experience working in the oil and gas industry, with experience in national oil companies and oil services companies. During this time, he worked on projects in Venezuela, Angola, Mexico, Sudan, North Sea, and many others. And during all these years, he has gathered great skills in reservoir engineering, reservoir characterization, dynamic simulation, lower completion modeling, improved and enhanced oil recovery, geomodeling, field development planning, and water management. And additionally, he had the opportunity to work on multiple heavy oil fields in the North Sea, UK, and tight carbonate reservoirs with heavy oil in Mexico. So during these development studies, Yamal managed to acquire relevant experience on heavy oil reservoir management and modeling. On the other hand, Yamal also has relevant experience in different types of reservoir fluids, such as light oil, dry gas, wet gas, condensate gas, and he has experience in clastic and carbonate reservoir. Nowadays, Yamal is also supporting Baker Hughes energy transitions projects related to CCUS, underground gas storage, geothermal, by combining reservoir technical service with multiple product lines in Baker Hughes. Yamal, please begin now.
Thank you, Dimitri, for the introduction, and thank you for everyone to allow me to have this time and present this presentation. So, as has been mentioning, this slide will cover the part of concerning well modeling for the geothermal resources, and essentially the contents of the presentation will consider initially one first step, which is of an overview of the geothermal reservoir modeling that consider or explaining in a high level the geothermal plate systems and also the type of geothermal reservoirs and general approach of the reservoir evaluation that is also important within the geothermal environment or geothermal space, and later on to simplify examples of how to build a numerical model for a geothermal. In the second part, we will extend more in detail how the temperature modeling is calculated or is approached in a well. And we want to understand the heat transfer process at the well level. Also understand the well modeling process and integrated system. And later on the point number 3 of this presentation, we will show some examples related to temperature modeling in wells and geothermal wells, especially. If we start with the first part of this presentation, I would like to give you an overview of geothermal reservoir modeling. So we want to take you from the big picture of the system into the small picture of the system, which is the well, that is which is the the item in the geothermal reservoir that allow us to communicate the fluid from the subsurface to the surface. But now, starting with the point number one, I would like to highlight the perspective of the geothermal system. And again, as you may know, and most of you has been involved, hopefully, in fields related to oil and gas, you know that hydrocarbon system or geothermal system, let's call it like that, has not the luxury of the hydrocarbon in order to define the accumulation that we have in the subsurface, because in the hydrocarbon plate system, we clearly have defined the rock source, the type of reservoir, and the trap. And with that, we can understand the amount of volume we have downhole. In geothermal plate system, we lack of this because we don't have any closure or any limit on the amount of fluid. And essentially, we want to understand from another perspective how we can implement or get energy out of a geothermal plate or reservoir. And in that regard, we want to understand or how we can utilize these plays by understanding like the heat capacity, and also understand how we can produce this heat out of the ground in an economical manner that can be productive into the system. I mean, into possible projects that are involved in geothermal. In that regard, we can also consider that a geothermal plate system, or a conceptual geothermal plate system, has many factors, and that we need to understand, right, in order to try to define what will be the possible amount of energy we can harvest from those geothermal places. And we need to understand the nature, for example, the depth of this heat source that we have in this geothermal plate or reservoir, and also like what is the dominated heat transfer mechanism that we have, if it's conductive or if it's for convection or for conduction. As well, we want to understand like parameters that are well known, like permeability and porosity, the type of rock mechanisms that we have embedded within those reservoirs, fluid rock chemistry, and also the recharge rate and source that we have. If we have, again, talking like if we have a heat energy that is coming from a near source of temperature, like a volcano or other source. And as well, we need to understand the type of play, right? As well on the exploration strategy, if we want to try to find out a possible geothermal plate system. Having said that, I mean, this table that is presented in here is just it's just a compile of the type of possible reservoir plate system related to geothermal that can be found when we try to develop a geothermal reservoir. And again, we divide, or the systems are the system I divide between reservoir that has convections or that are convection process dominated, or reservoir that are conduction dominated. And essentially, that process will be explained later on by my colleague Elkin. But again, it's to understand what type of energy or system we have in the reservoir, and how each one of them can provide a different source of energy when we try to produce those reservoirs. Again, this table is well known in the environment, or in the geothermal space, and it helps to characterize in an exploration manner the possible play that we have available. Now, if we move to the next slide, now we go into another point, which is as well important to understand. And again, as any process of trying to develop a field or a geothermal reservoir, we need to understand that we need to follow some essential steps that allow us to succeed on the way we want to develop those projects. And one of them is, as any other project related to geoscience or production, is data collection, because it's fundamental to try to understand from the data we have available the characteristic of the area, reservoir, heat source, if available. And then we try to get this information or this data into a building a conceptual model that allow us to understand deeply or more the characteristic and specification of the environment behavior that we are going to be dealing with. And with that, we want to also try to develop a numerical modeling that allow us to understand like the natural state of the just to name it, of the area we are exploring. And by definition, the natural state is to try to understand how the temperature was increasing or the system was heating up before we have any human intervention. And we want to understand that because we want to see how the temperature from which sector of the area is providing this energy of temperature to the system we're trying to develop in a geothermal project. And once we have defined it, this kind of understanding, we want to understand the productivity of these possible sources, right? And how efficient they will be in the future. Because at the end of the day, we want to understand by producing those geothermal plays, how long they will be in production and how efficient they can be in production. And by having said that, this is a bit more in detail what we are trying to look on the data. And essentially, we try to understand from the data source, like structure, lithology, and stratigraphic condition if available. Also, we want to understand the chemical composition of this water to understand if we can have any challenge on reaction when we are trying to produce those hydrocarbon places, those geothermal places, and also how it's going to be the heat mass flow transfer measurement from the downhole and into the recharge system. And also we want to understand at the surface condition what type of information, thermal information we have that can allow us to understand better the subsurface. And apart from that, we want to understand also information available in well logs, from well logs, temperature and pressure profile, and also flow rate, and help us to estimate characteristic of the production and also the enthalpies that we will have available from those geothermal systems that we try to. And once with that, we have this characterization in place, we want to jump into trying to build, as I mentioned to you, a conceptual model in where we, considering all the available information like lithology, type of rock, temperature, and parameters like thermal conductivities related to those rock systems that we have in the geothermal. We want to try to build a model that helps us to understand, again, the temperature properties, the direction of the movement of the fluid when we are producing or injecting or just producing fluid, and also how this inflow-outflow zone will be performing, like if we have a convection processing where by changing on temperature, when we do the injection production process, we have buoyancy effect that create changes on temperature downhole. So we want to understand those phenomena so we can try to maximize the capability of these geothermal assets that need to be developed. and as well to understand temperature and also the effect if we have two-phase zone, for example, steam or water in the system. And lastly, we also want to understand by creating a numerical model, as I mentioned before, the physics, right, on the system that we are trying to exploit, right? Essentially on the natural state, like how the temperature was rising from before any human activity to the point we try to put those geothermal reservoir in production. And we want to understand that because we want to design and optimize the geothermal system that we are trying to develop, and also predict the behavior, as I mentioned before, of temperature and pressure, and also the change of possible chemical reaction or situations downhole that can affect or jeopardize the geothermal place, especially as well understand the impact on the environment, and also try to define what will be the right follow-up in number of, for example, injector and producer, just to mention a case that we can implement. And also one of the as well important aspect is to understand like the economic feasibility, and also how to perform this project in where uh, the process of producing and injecting is economically valuable as any project that need to be developed in the geothermal environment. Now, with that in mind, I would like to show you two simplistic process or modeling that has been performed in the past. And essentially, as any project in the planet, we want to try to predict how will be the performance of the geothermal system, right? And essentially, in here, I'm presenting you a project that has been performed in an area in United States, and essentially is a basic model with a specific characteristic, right? And we try to, as I mentioned to you, embedded information of pressure, temperature, rock properties, and also available information to understand temperature and pressure and other parameters like uh, uh, the uh, the energy source that we want to measure from here. So essentially, this model, which is a simplistic one, help to predict, for example, information of megawatts that are available, or the change of enthalpy that we will have, and also the change of pressure and temperature that we could have for the process of producing and injecting, this case, the system. And in the next slide, which is slightly a more complex model, we have in here a model that has been built in where we have two distinctive energy zones, and we want to identify the possible temperature gradient differences in the model. So in order to get to that point, we have to start from the natural state process, in where we try to understand how the temperature profile that we have now in the system has reached to that condition, and we try to implement through process of simulation, dynamic simulation, how the temperature was changing through time that allow us to have what we see currently in temperature profile. And essentially, why is that? Because we want to understand things like in where we have to place the producer and injector wells, and how this temperature will keep constantly increasing or decreasing through time. Because essentially what we want to measure from this system is the temperature, the energy supply that we can obtain out of the production of this system, or hot water or steam coming out of this reservoir. Uh, Essentially, this is what a dynamic simulation, as well as any information available, is try to supply into any geothermal as project that allow us to understand how we can maximize the efficiency of any of those assets. With that in mind, I will pass into Dimitri, who will present the next presenter.
Thank you, Yamal. And if you have any questions to Yamal, please click the Q&A button at the bottom of your screen to send a question. And I'm pleased to announce our second speaker. So Elkin Santa Fe, he has over 20 years of experience in subsurface modeling engineering. He specializes in the application of numerical reservoir simulation and new computational technologies to support integrated reservoir studies, field development planning tasks, resource assessment, and secondary recovery. Elkin's experience includes projects in basins such as in Colombia, Ecuador, and the Gulf of Mexico, working for the Colombia Institute of Petroleum as external consultant, at Schlumberger as reservoir engineer for the information solutions segment, and at Best Energy as senior reservoir simulation engineer. He currently is a reservoir engineering discipline advisor, Gaffney Client Energy Advisory Team at Baker Hughes, supports regions Europe, North Sea, Caspian, and Sub-Saharan Africa. And his role involves the application of numerical reservoir simulation and classical reservoir engineering on critical projects related to CO2 utilization and storage, geothermal energy assessment, oil and gas, underground gas storage, and other activities. Elkin holds Master of Science degree in System Engineering and Computer Science with degree in petroleum engineering, both from the Universidad Industrial de Santander, Colombia. Elkin, please, you may begin now.
Thank you, Dimitri. Thank you, everyone, to be here. Well, following the path of the tidal system, what I'm going to do is to talk about the next element into the tidal system, which is the well. But for doing that, I will do a preliminary introduction about what are the main mechanisms that getting involved into all of this physics that we are trying to represent at the subsurface level. So before to starting and to explain what happens in the well, I will be briefly referred to the heat transfer mechanisms that govern all the process of heat conduction, of heat transfer, which is basically conduction, convection, and radiation. To begin with, we can understand the heat conduction as is the process by which heat is transferred through direct contact between the molecules of a body or a substance. The molecules impact each other, thus transferring heat between them. And conduction can occur in solids, liquid, and gases. Solids conduct more efficient because the molecules are much closer together than in other states. Here we can see a table that refers to the thermal conductivity of different materials. Remember that thermal conductivity determines a material's ability to conduct heat. And if, for example, we compare wood with silver, we can see that wood has a relatively low thermal conductivity, while silver has a high thermal conductivity. This is telling us what if we expose the same amount of wood and silver to the same heat source, wood will conduct heat more slowly. So therefore, we say there is a thermal insulator, while silver will conduct heat much more quickly. Therefore, we say there is a good thermal conductor. In another example, we could look at the case of air, which is a gas, and it is also has low conductivity. If we have an oven at 200 degrees Celsius, for instance, in this case, both the grill and the air inside the oven are both at 200 degrees. If we put our hand in the oven without touching the grill, we feel that the air is hot, but we do not burn ourselves, even though it is at 200 degrees. And this is again because the air is a poor conductor of heat. So the heat doesn't pass easily to our hand. However, if we try to touch the grill, which is at the same 200 degrees, we will burn ourselves since the metal is a really good conductor of heat. Moving onto another heat transfer mechanism, now we have convection. Convection is the transfer of heat by the movement of the mass. This occurs in fluids, and this implies that we will only find it in liquids and gases. We can divide into two mechanisms of free convection and forced convection. Natural convection or free convection, it is a mechanism in which the fluid motion is not generated by an external sources. Instead, the fluid motion is caused by buoyancy. So the difference in fluid density occurs due to the temperature gradients. In other words, we're saying that the motion of the fluid is caused by density difference, which in turn are products of temperature difference. This means that in nature, natural convection is much more than forced convection. So for the case of forced convection, it is a special type of heat transfer in which the fluids are forced to move in order to increase the heat transfer. This forcing can be done by external sources like a ceiling fan, a pump, or a suction device, or any other. Now, let's talk a little about the last heat transfer mechanism, the radiation. And we can define radiation as the heat that is transmitted by means of electromagnetic waves. Some characteristics of this type of waves are that they do not require a medium to propagate. So that is that they can even move in a vacuum. And also they travel at the speed of the light since they only transport energy and not matter. So in that way, all bodies emit radiation regardless of their temperature, which means that even we, as human beings, emit electromagnetic radiation because we have temperature. So the higher the temperature of the emitting body, the greater the amount of radiation it will emit. There is a proportion between the amount of radiation emitted and the temperature, and this will imply that a small increment in the temperature of a body means a significant increase in the amount of radiation that the body emits, and that is because this relationship is defined by an exponent in the temperature component. For example, an anvil that is in a room temperature of 20 degrees will emit a certain amount of radiation. However, if we add the heat to it and increase its temperature, let's see, to 100 degrees Celsius, the amount of radiation it emits will be greater. And in the same way, if the temperature continues to increase, for example, to 300 degrees, then the anvil will emit a much greater amount of radiation. Now, all of these concepts can be found mathematically defined in three fundamental laws associated with each heat transfer mechanism. Fourier's law, the model that describes the conduction heat transfer mechanism. Newton's law of heating and cooling, which help us to describe the convection, and Bione's law, which represent the concept that we have been described about radiation. This is something that you can explore further on your own. There are many interesting things that we could analyze here, but what I want to do now is to connect this little theoretical framework that you just walked through with our problem, and it is understand how this mechanism occurred in the well. If we think about the fact that we are producing or injecting hot fluids, all these heat transfer theory should be applicable to these problems for sure. So what we see here is a road schematic of what the well producing fluids from a reservoir can do. In a conventional situation, we know that the temperature at which these fluids enter into the well can be low, medium, or high, but certainly much higher than the surface temperature. And we also know that there is a temperature gradient associated with the layers of the subsoil. And in the general geodynamic mechanisms, the heat is transferred from the interior of the air to the crust. So in this scenario, it is clear that there are temperature deltas everywhere. Also, there is a movement of fluids. And all of these elements lead us to think in the heat transfer mechanisms that can be present. For example, we will have heat conduction in the formation, in the cement that fix the pipes, and in the same wall thickness of the pipes. Since the fluid is being produced, there is a pressure difference along the pipe, which will generate movement of that fluid, and consequently, we will have forced convection. Convection. Additionally, in the annulus, there are also retained fluids there that may not necessarily be in motion, and that will depend on the type of completion that is done and the way in which the well is operating. But for example, in this diagram, we have a plug in the lower section. So we could think that these fluids that are here are not being affected by movement. However, they can gain or lose heat. As we said before, this temperature difference impact the density, generating movement and heat transfer. So here we will have a case of a natural convection. Finally, we could have radiation between the walls and of the pipe, since we explained before, anybody that is at given temperature emits radiation. So all the mechanisms are grouped together, and the task now is to put this into a mathematical model that allows us to make estimations of the temperature condition of this fluid inside this production or injection pipe, if applicable. So first thing that we are going to do is take a diagram of our well, and we are going to discretize it into small segments. This is going to help us to perform a discrete analysis. Then we're going to do is to extend that analysis that we are doing in that small control volume to the entire section of the well. In this control volume, we will have a mass flow inlet and outlet, since we are producing a fluid from the reservoir. And in turn there, we will in turn there will be a temperature difference between these 2 points. So the fluid within this control volume could have an average temperature. We can put it in that way. And this will contrast with the temperature of the surroundings and the formation also generating a temperature delta. So this direction is what interesting us, because we want to see what we want to see is how much heat the fluid we are transporting to lose or gain through the interaction in the environment, with the environment. So there is no work like the one we know from thermodynamics of the piston type, for example, acting here. So we can remove that dam from the original equation. In the next step, what we do with our model is to take it to a differential form, because we are going to assume that liquid is incompressible. We're producing liquids. To simplify the analysis, the term representing our kinetic energy change will become 0. This will leave us with only an equation that depends on the enthalpy difference between 2 points and the potential energy, as you can see in the lower side of the slide. Now we adjust to a section where we know some state of the system. We could place this control element, taking as an edge the node that is in the reservoir, where we know the PWF and the temperature of the reservoir. Balancing the unknowns and knowns variable, well, in this case, we know the enthalpy at the point 1, because we could know this pressure and temperature from the first node. And if we consider that this node is located in the reservoir, that is a condition that we can resolve. The general model includes an expression that allows us to express the total enthalpy of if it were something similar to a mixing rule, where the fraction of each phase is presented multiplied by the enthalpy of each phase and will give a degree of contribution. In this case, we are talking about a water-dominated system, so we will simplify the other phases present in the equation. The delta zeta can be equal to delta L for a vertical well. We can estimate the mass flow rate by using a reservoir model, maybe a simulation model, as Jamal already explained, or maybe by using a simplified reservoir model. And the pressure in this volume for this proposal of the mathematical development, we are going to assume that is known. So we are not going to worry about the way in which the fluid flow is causing a pressure profile, because that is another part of the multiphysics that compose here. So we are going to focus just on the thermal aspect. So all the pressure profile, we are going to assume that we know that. So we are left with the heat flux and the enthalpy at the point 2 as unknowns. So by solving the enthalpy in this point 2, and taking the pressure in the point 2, remember that we already said that we know the pressure profile, and assuming that temperature in that point 2, we could estimate the enthalpy, H2. However, this calculation led us to an iterative process, and this is something that we can manipulate in another way to avoid that iterative process and to go more straightforward into a physics described in the model. So this heat can also be expressed as a relation of the temperature difference between the fluid and its surroundings, multiplied by the effective heat transfer area, and also multiplied by a coefficient that we will explore in the further slides. This is the general form of the equation, but the details will vary depending on the heat transfer mechanisms that we wish to represent. So taking the heat flux expressed the way that we saw it is just now, the first term that we have that we can break down here is the area. What we have is a simple cylinder that is the physical shape of our control volume. Its dimensions are associated with the dimension of the pipe. However, it is important to note that we don't just have a tube here. If you remember the schematic diagram of the well that I showed you earlier, we have a production tubing casing. The casing is cemented, and this whole arrangement is bonded to the rock throughout the cement as well. So actually, the heat will cross all these layers from the axial axis of the well to the formation, or vice versa. So this will lead us to define between which zones we will have conduction, convection, or radiation. And in this case of conduction, we will speak of a thermal conductivity, which in many of the cases is more of an average conductivity. In the case of forced convection, this convective coefficient will have a strong dependency of a mixture between the Reynolds number and the Prandtl number. And for the case of natural convection, we will also have a contribution from the Prandtl number and the Grashof number. So in the case of convection, these convection coefficients themselves are dependent on temperature. Therefore, we will also require an iterative process to find their value. And finally, if we consider radiation, this coefficient will also have a dependence on the Stefan Boltzmann constant and on the emissivity. Now all of these dynamics coefficients will be encapsulated by by a unique component or element, which we call the overall heat transfer coefficient, which will also have a geometric dependency, so to speak, in relation to the radius of coverage from the axial axis that we, as we can see in the diagram. For purposes of this analysis, we are going to focus on conduction and convection. The thermal conduction and convection is dominant in case of liquid filling in the annulus. So thermal radiation can be ignored. But I have to clarify that if we wanted to increase the complexity, we can do so, and we can include this element given the radiation is given that the radiation is considered to occur only when the annulus is filled with gas or vacuum, and this will not be the case for this analysis that we're going to develop. But if that is necessary, the model led you to include in some way. So returning to or representation of the well with the layers, and considering the different mechanisms involved, we can express this heat as convective or conductive, depending on the region that we are crossing. So here is an example of what this sum of effects looks like, depending on the layer that we are crossing and the general equation that we apply to each of them. And here we can see the complete mathematical development for the layers in the example that I posted of the previous slide. I will say that it is mostly of a matter of applying algebra and reorganizing the terms, to clear the temperature deltas, identify the elements of the main equation, and next to reorganize the elements. But this expression already basically has a temperature delta between the fluid, which will be its average temperature, and the well phase, which we can assume could be the temperature of the surrounding formation. We already know that this is not totally true, since there is also a temperature profile inside the rock. But since we are trying to build a relative simplified model to understand what is happening, this assumption is valid. The red expression that you can see here represents the combined effect of all the coefficients of all the heat transfer mechanisms present in the situation. Now, this expression is just an example. It basically correspond to that condition where we have the tubing, the annular, the casing. If the shape of the well, not the shape, the completion configuration of the wall change, this expression can change as well. Note, for example, here we have not represented as insulating coating, which is something that is associated with the completion of a geothermal well. However, I think that this is an example. This case illustrates the idea what is behind that variable color overall heat transfer coefficient. Here we can see what this coefficient looks like, isolated from the equation. Again, this is an example for the wall setup we did, but the important thing here is to understand that there is a direct relationship with the heat loss. If U is low, heat loss is low, but if it is high, heat loss is very high. So understanding this helps us to generate the models and the temperature profiles in a well. We can assign values within a range to create awareness and avoid delving into the term-by-term estimation of the U value. So with this in mind, and going back to our initial analysis, we have two equations, two ways of expressing the same heat, and now we are going to combine them to generate a mathematical model that describes the temperature of the fluid along the well. Now, talking about the solutions to this equation, the Rame equation is one of the most well-known and widely used analytical solutions and implemented in different software modeling tools. it has reported very satisfactory results that match with the field results. So let's take a quick look in the components of this equation. In this case, T8 represents the injection or production bottom-hole pressure, temperature. We have a geothermal gradient represented by a linear expression with the physical coefficients A or B that usually are associated with temperatures at surface or measuring at the subsurface. Zeta is the true vertical depth. TO is usually the unknown variable, and most of the times, in many, what is expected is that time dependent, because this temperature for sure will change with the time. But we can simplify the model in order to make an approximation in a steady state. The relaxation coefficient is primarily a function of the overall heat transfer coefficient and mass flow rate. So in this equation, in this particular equation, Cp is the specific heat of the injected or produced fluid, and M is the mass flow rate that usually come from the reservoir models or the geothermal reservoir models. K will represent the thermal conductivity of the formation, and Td is the dimensionless temperature function as a logarithmic expression. So with this model, in general, we can describe the temperature profiles in terms of the potential losses that we have in the well along the geometry that this well usually has, and according to the general properties that describe thermal properties that describe the borders and the elements that compose the system. So now if we consider all the nested components, we have an integrated system. We have the reservoir model, which represents the underground geothermal system. This connects to the surface through our well model, which refers to the production and injection processes within the well. And this model in turn provides an input to the surface model, which is basically made up of the geothermal plant, as in this case in the image, but this represents the ORC power block, but it could also be a plan for heating projects if that is the case. Now, the abstraction levels of each system can be as complex or simplified as the situation allows. So the model, the development that we saw in the previous slides is a simplified model. There are ways to be the same well model in a more elaborated manner, more numerically orientated and much more organically integrated into the reservoir model, especially when we talk about situations where we can build simulation models like the ones Jamal was presenting at the beginning. The major drawback here is that the more sophisticated the approach we use, the greater the data demand will be. And when we talk about conducting exercise, when we want to get an idea or a first assessment, data is not readily available in many of the cases. So this is where these analytical or semi-analytical models can help to give us an idea of what the capacity may be, and we could establish connections between the components of the system that we are trying to include. Now, what we are going to do is to cover a couple of examples, a couple of cases on which we had the opportunity to work, and I would try to expose the main aspects of these cases according to the analysis that we did. Here, first case, in the context of this problem, the goal is to compare two well trajectories. So the need to compare them arises because there is an interest in developing a heating project. To develop this heating project, a formation is in mind, and that will serve as a geothermal reservoir. But the problem is that accessing that target requires a directional well. So now the project owns the location and has the facilities installed to distribute dissolved water. Additionally, they have some wells that serve as a reference in terms of pressure, temperature, and flow rate. And it is known that reaching the target through a directional well has an associated cost, but there is also the option of purchasing the land that allows for a drilling a well more directly. So in that way, you could reduce the drilling costs and potentially hit losses along the well. So in this scenario, the modeling work begins by analyzing the available evidence and establishing reference points. As I mentioned before, in this particular case, there are pressure tests from nearby areas, temperatures, and fluid flow profiles. The trajectories were designed based on the available reference, and then all of this was used as an input to calculate the temperatures. At this point, we establish a thermal gradient by using the points that we already have, and we run some sensitivities, assuming rates and overall heat transfer coefficients. Since we are using a simplified steady-state model, we will not model over the time, although we will introducing the completions defined for the design of each well. We will generate sensitivities by using the overall heat transfer coefficient as a moving variable to try to represent situations when the internal and external insulation conditions could be excellent, average, or truly poor. With this, we can establish a necessary matrix that allow us to have a range of flow rates and favorable isolation conditions, giving us an idea of what the head temperature may be depending of the well trajectory option. That was the ultimate goal on this exercise. Now, with this framework in mind, we can move onto detail engineering and begin designing the internal isolation scheme, or understanding what the expected reservoir capacity should be by adding complementary analysis like the nodal analysis, for instance. In this second exercise, the goal is to review the reservoir's potential. This is in the context of geothermal energy, because in the previous case, well, the designs and available information are used to estimate the wellhead temperature. However, what I want to emphasize more in this case is the level of uncertainty that we may face. Hence, the importance of evaluating the reservoir using simple models. Here, as you can see, we want to know which reservoir will have the best potential, but at the same time, each reservoir represents a base case, a minimum and a maximum from the perspective of reservoir quality. We are not using a simulation model here. We opt for the use and application of reservoir models that implement Darcy law, such as those based on IPR, taking advantage of the fact that we are not considering a phase change. Therefore, after the stabilized test data point, we won't necessarily experience behavior like that the model by Vogel equation based on the compressibility of the fluid is trying to describe. Here, speaking in general terms about the workflow forward, we use the information for each reservoir, the completions type that were defined for what will be the well and the pressure and thermodynamic condition information estimated for each case. And what we are going to do with all of this information is to perform a classic nodal analysis, generating a number of cases and estimated the AOF could AOF point and the operating point according to each case, and generating the recommendations based on that for each case if we found more than one or two candidates. In order to apply this model, in this case, we require that the system be defined as water dominated, and that is a condition that we have to check in a preliminary way. Since this condition doesn't apply the entire scenario and the model change, because as you could see in all the mathematical development, we condition on the model to be water dominated. That is why the model has the way that you could solve in the previous slides. So that is an important element that has to be checked before. And the reservoir models that we select are Darcy type based on the IPR, as I mentioned earlier. Given the water-dominated condition, we can apply it without any problem, since the system condition doesn't not consider phase changes. And that is why we see this extension of the straight linear behavior after the stabilized test data point. Finally, we can present the different scenarios with their operating points and proceed to compare which reference offers the best potential. If you notice the main difference with the first exercise, for example, that is the case one, we already had well test rates that gave us an idea of how the flow rates will behave. And in this case, case two, we don't have that reference and it must be created. So for that, we use the well model integrating and simplify the reservoir model. The goal is basically to have the lowest possible temperature lows, and to reduce that lows along the wellbore. A high rate is usually very favorable. What I mean is that it is not just a matter of insulating the wellbore very well, but also of achieving a flow rate that can carry enough heat to the wellhead, and high rates are usually very favorable. And one way to achieve this is by changing the type of completion, changing the casing or tubing configuration, which are analyzed and which are analyses that we can perform to make recommendation in this regard. But we can also consider the use of artificial lift systems, such as the ESP pumps, which will allow for higher rates and moving the performance, for example, to this area, and getting in some way and in improving of the entirely integrated system, and in that way we can get more energy from the subsurface. In this case, case 3, what I want to show now is how we could connect all of this with a simple surface estimation. Again, we have a situation where we use the available information, supplementing it as it is needed, as appropriate. And here, even flow rates are being assumed, and conceptual trajectory is being considered where the well has a 30 degrees deviation. It's a scenario that was applied to this. With this information, we proceed to estimate the heat temperatures and sensitize flows and thermal properties. These simplified models, perhaps the most influential parameter is the overall heat transfer coefficient. It is one of the most sensitive parameters, given that the final completion conditions of the wells are unknown. But therefore, under this situation, we do not always calculate the value of this coefficient with the equation shown in the previous slide. Instead, we use a simplified form of the well model to run the scenarios quickly. So now there are computational tools that allow us to test heat losses more precisely, but they also require all the details of the final well configuration. That is one of the key elements that we need to have available. Here we can also see what I was saying a moment ago, how the high rates or the increment in the high rates the increment to high rates can be beneficial in order to 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 get a reduction of temperature losses along the well. And in these profiles, you can see the temperature of the conceptual trajectory, the profiles of that trajectory that I showed a moment ago, and how they change depending of the flow that we are assigning and the coefficient transfer that we are applying. Now, with this in mind, we can take the exercise a little bit further. If we assume that we use the heat that we are extracting to exchange it with the ORC plant, we could estimate how many megawatts electricity we could get from the reservoir that we are trying to evaluate. And this will help to us to sensitize different scenarios. Here, for example, we have an estimations of the energy rate at the wellhead, meaning it is an instantaneous energy rate given in megawatts thermal, which give us an idea of how much energy that volume of fluid carries at that point in the system, right? So this is a kind of instantaneous energy measure. So the important thing here is understand how much or how what amount of energy can be captured at this point. So, and that will depend greatly on the return temperature that we are going to have to the geothermal reservoir. So here we see roughly how can we estimate how much energy in megawatts thermal, and how much of this energy can be delivered to the ORC plant, depending on the return temperature that we are going to have. With this energy exchange between the geothermal fluid and the ORC plant's working fluid, with this difference multiplied by the plant's efficiency, we can get the potential electrical value, megawatts electricity that we could obtain from the system integrated in this way. So now let's keep in mind that the maximum theoretical efficiency of these plants will be determined by the Carnot cycle, and it isn't very high. But this gives us an idea of how we could perform an assessment exercise in an integrated environment. So as we have seen, a well model, even a simplified one, can offer us the opportunity to explore what if scenarios, especially in situations where the information is scarce and where we have to make assumption across all points of the system. However, we still want to have a general idea of what our system capacity may be. And it is important to remember that a simplified model has restriction, which is why it is simplified, but that doesn't mean that it is any less usable. These models won't be able to measure more complicated elements such as temporary variations in flow. Well, in some cases, yes, if we do a more elaborated model, but not in the case of a very simplified model. And also, for example, we cannot measure the cooling effect that can be affecting the reservoir, and according to the return temperature that we are getting. I insist they can give us a preliminary assessment that let us to propose information capture plans, for example, and detailed engineering studies, or find some critical points in advance, such as the absence of hydraulic capabilities in the reservoir or extreme temperature losses, even by using overall heat transfer coefficients favorable for well isolation. Yeah. So I think that in general terms, okay, all of these elements putting together and working in a very well methodology can help to us to create that big picture that we want to create. Okay, so I think that we can hear some question and try to clarify
Yes.
more some aspects. Yep.
Yes, Elkin, thanks very much for the presentation. And yeah, it's now time for Q&A session. And if you haven't sent a question, please click the Q&A button at the bottom of your screen to send in a question. And also please use this QR code on your screen to complete a brief survey about today's presentation. Right. Okay. So yeah, let's proceed to the questions. Elkin, I think the first one is, you showed lots of parameters that influence temperature modeling in a well. How do you think, what are the main uncertainties regarding the input parameters that we apply for our calculations? And what are the main risks associated with these uncertainties, and how do you think we can mitigate these risks?
Yeah. Well, one of the critical aspects correspond to the parameters. Sorry, corresponds to the overall heat transfer coefficient. That is one of the more sensible parameters in the model, and the uncertainty associated to this parameter is associated to the final configuration of the well. I'm talking about the final completion that we are going to apply. In the context of the preliminary studies, there is many sources of data that are not precisely complete. Let's see, sometimes we don't have a clear description of the temperature gradient. Sometimes we are not quite clear about what can be the flow capability of the reservoir, which lead us to get uncertainty in the flow rates that we are going to use. And basically the way in which we try to mitigate this parameter is by using analogies in terms of areas that were explored close to the area of interest that we want to evaluate. For example, if we have a hydrocarbon field close to the geothermal area that we want to analyze, we can take some data from that wells. If we know an preliminary study that can give us an kind of a special geothermal gradient that we can apply it in the area, we can use that. And in terms of the overall heat transfer coefficient, what we usually apply this is a sensitized, as I show you preliminary, that cover a range between poor isolation and the best isolation as possible, in order to get the two extremes, the two main extremes as possible of the range of the elements in the parameters that we are using in the model.
Thank you, Elkin. While we are waiting for other questions from the audience, so you showed us a case when there was a scenario where you modeled well placement, right? Geothermal well placement. So what do you think are the main challenges when it comes to model several geothermal wells, and how we can estimate the best possible location if we drill several wells in the geothermal field?
Well, in the case that I exposed when I was comparing the two trajectories, this analysis was applicable because the only thing that we want to do was, I think that probably that is the case that we are talking about. I'm not sure, or probably it's the second one, but let me just point in both of them quickly. If the case is more related to the first one, you know, the point here is to try the loss along the trajectory. So to 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 look for elements that let us to try in terms of locations, aerial locations. I think that probably a model like Jamal was explaining at the beginning is better. And that is because a model like that offers the possibility to analyze the transfer of heat in three-dimensional space, in three-dimensional models. Because in this case, basically, the transfer of heating is unidimensional. Just is one-dimensional. It's along the well, right? So the estimation will follow that physics. But if we are pursuing to try or explore what is the best location just based on the trajectory, that can work, right? But if we are exploring in terms of areally, you know, what can be the best location in terms of, okay, let's explore in all of this area, probably a 2D or a 3D model should be more suitable for doing that.
Thanks for the answer. Okay. Okay, so yeah, and we have another one. So we have different geothermal system now. So we can use enhanced geothermal. We can use advanced geothermal closed loop systems. So how, if we consider these scenarios, what are the main differences in your approach between, you know, modeling conventional geothermal system and, for example, advanced geothermal system? What do you think are the main challenges and differences between these two scenarios, cases?
Well, the main difference that we have been detecting internally in the team is the challenge of data. The simplified approach led you to get a big picture in terms of what we can say, okay, we have less variables. Let's see a little bit more of control in that variables because the level of uncertainty associated due that the lack of information is quite high. I will say that if we pursue a context with a more complex physics involved into the model, probably we will get better elements, you know. So and there is the difference like, okay, I can model the system along the time. I can model the effect of cooling of the reservoir. So in that way, I can, for example, play with the position of the injector and the producer if we are evaluating a situation like that, because I can, for example, get a geometry about how the cool front is moving along the reservoir. That is something that we cannot do with these simplified models, right? But in addition, if we are pursuing a study like that, with that level of sophistication, we will need to get, you know, enough data to create a proper 3D model to evaluate that situation. And that is something that that sometimes we don't have because we have just a couple of points, some gradients, and sometimes there is not a spatial distribution of the quality properties of the reservoir. I think that there is the main difference, you know, the use of the model and the purpose of the model. In these simplified models, we are thinking more, more in a early assessment, preliminary assessment, you know, and that leads us to detect critical points and to prepare, you know, the further studies that we want to pursue in order to elaborate more sophisticated models.
Thanks, Edgar. So a question from the audience. There is a heat recharge rate based on heat conduction. The temperature at the wellbore decreases over time. This is a well-known effect in geothermal wells. How is the model predicting the time before the well outruns the heat conduction delivery to the well? Could you please, you or Yamal, comment on that?
Yamal, if you want, or
yeah, Dimitri, and the audience. Essentially, so when we try, as I mentioned to you in the slides, we want to understand when this, lack of energy or heat will decrease. I mean, when this heat will decrease near wellbores, right? And essentially, with the models, with dynamic simulation, which is one option, so essentially, we have to include information of, for example, properties, as I mentioned, and also uh, uh, thermal coefficients of the rock, and also how the system heating entirely. So what we want to see, if I put you one simple example, is we have one producer and one injector, because we are trying to produce on a system that is that has, let's say, it has high enthalpy. So we know that possibly we will have steam at surface. So essentially what you wanted is to try to keep pressure in the system that you are producing, and also try to keep the temperature. However, when we are doing this process of producing and injecting, the temperature of the fluid that we are injecting into the reservoir is of course lower than the original one we produced. And what we want to measure is how fast or how quick this cooling effect will reach the producer, that will decrease the amount of, let's say, enthalpy, or translated to to joules, and then translated to megawatts of surface, can affect the entire system. So essentially, we try to measure how the fluid movement or cooling effect is traveling in the subsurface from the injector to producer, to give you one example. Another one could be that, for example, if we are in a enhanced geothermal system in where we create fractures to try to harvest this energy, in where we are injecting fluid and then producing from another system, we want to understand how quick, if we have, for example, a conductive system, how fast this fluid can be heat up, and what will be the temperature that we can reach, that can be reached at the producer. So this is our aspect that can be observed in dynamic simulation. Essentially, it's just pores media calculations through fluid movement and a three-dimensional calculation to identify the change of these parameters that are governing the dynamic simulation. Hopefully that answered the question.
Thanks, Yamal. Yeah, and if we can switch to a more general question from the audience. How do you think difficult would it be for a petroleum engineer to, transition to geothermal industry? And what are the challenges here? So can you provide advice to petroleum engineers if they want to, try to work in geothermal area?
Yeah, I can handle this, Dimitri.
Okay.
So essentially, well, if you think about it, petroleum engineers are well prepared to embark themselves into the geothermal industry. If you understand, I mean, as a petroleum engineer, you try to understand the fluid of the movement of fluid downhole. The only difference that we will have, or the only difference is that when you go and be into a geothermal space or geothermal industry, you have just a one single fluid, which is water, that can be either seen in a phase condition, in a gas condition, gas phase condition, if the pressure and temperature has changed from hydrostatic condition, or you will see a single phase which is liquid downhole. Essentially, the rest of the item that govern the production of any hydrocarbon reservoir are exactly similar to the one that cover the geothermal industry. Now, aspect that you need to learn is that we are not going to be considering like how much hydrocarbon we can produce. It's going to be considering how much energy we can harvest. Now, in the market, in the way to learn about geothermal, we have plenty of sources and books. For example, there is multiple books related to reservoir engineering, for example, related to geothermal environment, in where you can clearly understand the challenge that the geothermal industry face compared to what we normally see or you see in the oil and gas industry. Again, it's a process of starting from understanding, first of all, the single aspect that we have in common between the oil from the petroleum engineering side to the geothermal area, and the other aspect are understanding the technologies and also the different approach to produce any geothermal reservoir.
Thanks, Jamal. Elkin, any comments on this? I think you also have petroleum background.
Yeah, well, I remember my own experience. You know, in 2000, in 2017, I started thinking how can I start to think in the way in which the experience that I have been acquired in reservoir engineering and reservoir simulation can be applied to these geothermal problems as an element, you know, of let's see, as an element of expand, you know, my horizon, my technical horizons. And what I notice is that in many of the challenges that geothermal is facing currently as a petroleum engineer, and in terms of the experience that I have been acquiring on this area, there are many things that we can apply. Even the tools that we can use to model the geothermal systems can be applied from the same oil gas systems that we model, and also there are many fundamentals that we can apply here in order to analyze the behavior of these systems. So I wouldn't say that is quite straightforward, but there are many understanding that can be applicable and very useful. And one thing that is also quite important is that there are many people that is interesting on to see what is the geothermal, the potential that there is in an area, but most of them doesn't have a complete understanding of what is happening in the subsurface processes, and that is something that a reservoir engineer, a petroleum engineer, a geologist can put on the table as a value added in
Yeah,
terms of
and
these studies.
that's why these sessions are also important. Okay, thanks for your comment. And I think we can have another two questions. Next one is from the audience. Excellent presentation, very comprehensive approach. Were the examples presented real case studies or synthetic? If real, what kind of decisions can be explored based on these analytical methods, and what would be the next steps to carry out?
Well, the cases that we present, all of them were applied. Yeah, all of them correspond real cases. We just take some extracts of these studies.
And what are the next steps based on the results of these models?
Well, in some of the cases, the next step has been, to pursue the plan of data collection that we suggest, or even to replan the strategy in some cases to make a better evaluation. Yeah.
Thanks, Elkin. And yeah, probably the last one from the audience. So for the model, if you were to shortlist, what would be the list of inputs or types of data necessary to adapt the model to any location or geothermal field? I think that's related to the slides that Imal showed, with the data required.
Yeah, Dimitri and Nico, I can see. So the shortlist, I mean, information needed is especially temperature profile, pressure, structure, and rock properties, right? And also understand from the play how the temperature is changing through time, and understanding how you can understand the change on temperature. But essentially, it's going to be pressure, temperature, the property of the rock that you have in the system, the fluid characteristic, and possibly, if you want to explore further, the possible composition of the water and reaction that can occur downhole, to model that into a dynamic, to have that into a dynamic simulation.
Thanks very much, Imal. I think that was the last question. So yeah, over to you, Diana.
Thank you, everyone. Thank you, Dimitri, Yamal, and Elkin. Thank you, everyone, for attending today's webinar, for your participation and asking all those great questions. Please use the QR code that you see on your screen to complete a brief survey about today's presentation, and have a wonderful day.